Welcome back to our IB Physics video series. This is the first video in IB Physics Topic 7, Atomic, Nuclear and Particle Physics, where we will be looking at evidence for the atom, electron energy levels, and atomic structure. You should already be aware of basic atomic structure from your NYP or GCSE courses, but you're expected to know a few extra details in the IB Physics curriculum. Let's go through it. In early atomic modelling, 3 individuals were very important: Democritus, Dalton, and Thomson. Democritus considered the structure of matter, concluding that if one kept dividing matter, one would reach a particle that is indivisible, i.e. an atom. Dalton then took this one step further and decided that matter could be divided into different elements, which themselves were composed of atoms of different masses. Thomson fired electron beams at electromagnetic fields, determining the size and charge of an electron in the process. Using this knowledge, he developed the plum pudding model of the atom, which was composed of electrons in a matrix of positive matter. Following these early models, Rutherford uncovered the nucleus of an atom via the Rutherford-Geiger-Marsden experiment. In this, helium nuclei, i.e. alpha particles, were fired at a thin gold film to attempt to find structures. Some particles went straight through the film, but others were scattered at huge angles. The alpha particles were already known to be positively charged, so the scattering suggested the presence of a strong positive charge in the gold film, i.e. the nucleus. However, the straight path suggested there was empty space between the nuclei. This formed the basis of the Rutherford model, atoms consisting of a positive nucleus surrounded by electrons in free space. Finally, Niels Bohr discovered electron energy levels, using this to complete our basic model of the atom, known as the Bohr model. He found that hydrogen absorbed and emitted only specific wavelengths of light. From this, he determined that electrons exist at fixed orbitals within the atom, forming the Bohr model. It is the most basic model we use today, and is covered later in this video. For now, we will focus on why fixed electron orbitals cause the hydrogen emission spectrum. As introduced in our Topic 5 video series, an electric field is exerted by any charge, including protons. So we can say electrons that sit in orbitals closer to the nucleus will experience a greater electrostatic force than electrons that sit in orbitals further from the nucleus. Thus, if an electron is to be removed from the electric field, it would take exponentially more energy to remove it from a closer orbital than a further orbital. Furthermore, if electrons occupy specific orbitals, it must take a specific amount of energy to remove each one. This can be visualized as a converging line spectrum due to the exponentially weaker electrostatic force with distance from the nucleus. So how did Bohr observe this pattern? Well, when shining electromagnetic radiation on hydrogen gas and looking at the transmitted radiation, he noticed black gaps in the spectrum. This is called the absorption spectrum, because it suggests that certain wavelengths of light are being absorbed by electrons to be promoted to higher energy levels. Conversely, when exciting hydrogen gas using electricity and looking at the produced radiation, he noticed single lines in the spectrum that match the gaps in the absorption spectrum. This is called the emission spectrum, because it suggests that the same certain wavelengths of light are being emitted by electrons to demote back to their original energy level. The IB expects you to be able to calculate the energy of the absorbed or emitted wavelength and thus energy jump of the electron. If you take IB chemistry, you may already be familiar with the required formulas, which are energy equals Planck's constant times frequency, or energy equals Planck's constant times speed of light divided by wavelength. In these, Planck's constant is 6.63 times 10 to the minus 34 joule seconds, and the speed of light is 3 times 10 to the 8 meters per second. Let's practice what we have learned so far with a practice question. An electron absorbs a 1.7 times 10 to the minus 23 joule wave to jump energy levels. What is the frequency of the wave? The equation to use is energy equals Planck's constant times frequency. So, substituting in the values of energy and Planck's constant and solving for frequency, we get 26 times 10 to the 10 Hz, i.e. 26 GHz. Despite the Bohr model correctly introducing electron energy levels, it is technically incorrect. For those of you studying IB Physics higher level, you will explore the Schrödinger and Heisenberg models in our Topic 12 video series, which correct Bohr's mistakes. You've now reached the end of the preview for this IB Science video. If you want to check out the full video, head over to our website and select a membership plan today.